Now this one here, this section here, or this question here is about binomial expansion. So binomial expansion, which I'll write up here. So hopefully now that you know about polynomials, and you might remember binomials means that I've got two terms, and I'm going to be doing an expansion means there's lots of brackets involved. I've got this a plus b to the power of 5. Now, a couple of things that will help me out with this, with the knowledge that I might have, that I know that if I have a plus b squared, and if you expand that, because of course a plus b squared is just a plus b times a plus b, that's going to be a squared plus 2ab plus b squared. Because a times a is a squared, a times b is ab, b times a is ab plus b squared. So by that logic, a plus b cubed is just a plus b times by this answer up here. So using that sort of pattern and logic, then I know that if I had a plus b to the power of 5, that's going to be a plus b, and then what I'll do is I'll chuck one of these in here, and I'll throw in another one, because that's squared plus a cube and another squared, or times. So that already seems like a lot of work. I hope there's an easier and quicker way to do this. So let's go and start by at least expanding this lovely out. So a plus b to the power of 5. So what I'm going to do is I'm going to go and expand accordingly. So I'm going to start by at least getting these expanded. That will probably help me right now. So a times a squared is going to make that a cubed plus 2a squared b plus ab squared plus ab, sorry, that should be saying plus a squared b plus 2ab squared plus b cubed. And that's still times by this lovely friend out here. This is very, very easy to get lost in this quagmire of pronumerals, so make sure that we're following along. So let's simplify this. There's no other plain old a cubes. 2a squared b, is there any other a squared b's? Yes, there is. There's an a squared b, that's going to be a 3a squared b. Is there any ab squareds? Yep, there's one out here, that's going to be another 3ab squared. And then we've got a b cubed here. So I'm going to color code this section here. I'm just going to change the colors for each of these so that you can follow along with what I've done here. And then we will use this one. So when I'm multiplying, you know which one multiplied with which. So I'm going to multiply the a cubes with everything in the other one. So that's going to be a to the power of 5 plus 2a to the power of 4b plus b, a cubed b squared. And now I'm going to multiply this term with all of the others. So this is going to be 3a to the power of 4b plus 6a to the power of 3b squared plus 3a squared b cubed. And this is going to be plus 3a cubed b squared plus 6a squared b cubed plus 3ab to the power of 4. And then a squared b to the power of 3 plus 2ab to the power of 4 plus b to the power of 5. So now we just need to collect the like terms. I like to have little highlighters because I know they'll make life easier. Well, I know there's no other a to the power of 5s on their own, so that can stay there. Let's get my little highlighter out. Where's my a to the power of 4b's at? There's another one there. I think that's going to be the only ones. Yep, so that can go plus 5a to the power of 4b. Let's find my a to the power of 3's and b squareds. A to the power of 3, b squareds. There we go. Is there any more of them? There they are. So that should be right. Yep. So I think that's the only ones. Yep, so it should be 10a cubed b squared, because 6 plus 3 plus another 1 is going to make that 10. A squareds and b cubes, a squareds, b cubes, a squareds and b cubes. 3 plus 6 plus another one's going to make that another 10. Plus 10. A squared b cubed. And then we get these ones, so 3ab to the power of 4, 2ab to the power of 4. Is going to make that 5. And then we've got this b to the power of 5. So hooray, we've expanded it. But by golly, did that take a very long time. If you have a look at it, it has a strange pattern forming. You'll notice here it's got like a 1, because that would be what the number in front of the a to the power of 5 is. 1, 5, 10, 10, 5, 1. That's interesting. It also, you notice that the a's descend. A to the power of 5, a to the power of 4, a to the power of 3, a to the power of 2, a. Just as the b increases. B squared, b3, b to the power of 3, b4, b to the power of 4, and b to the power of 5. Well, thankfully, someone had, much earlier than us, had figured out this kind of thing, and figured out that there was indeed a pattern. Well, that was our good friend Pascal. He came up with a lot of lovely mathematical whatnots, and one of the things he came up with, which you may have heard before, is the Pascal Triangle. And the Pascal's Triangle works a little bit like this. You'll recognize if you haven't seen it before. So, if I've got a 1, I'll put another 1 and 1 here. And then what I'm going to do is I'm going to put a 1 here. Now, why the Pascal Triangle works, which you'll see here, is that as I'm making each layer into the triangle, I'm adding the two numbers of the previous row. So it's 1 plus 1 is 2. So similarly, this will become 1, 3, 3, 1. And similarly, because 1 plus 2 is 3, 2 plus 1 is 3. It's because 1, this will become 4, 6, 4, 1. It becomes 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, and 1. 1, 7, what are we, 11 now? No, silly me. 21, 35, 35, 21, 7, and 1, and so on. You could keep doing this for quite a long time. Well, what some other clever clogs, including, I would dare say, our lovely Pascal has realized is that there is a correlation between the Pascal's triangle and, of course, being able to do binomial expansions. So this 1 would represent a plus b to the power of 0, because you hopefully remember from your index laws that anything to the power of 0 is equal to 1. So that's going to be equal to 1. For this next one here, this would be a plus b to the power of 1. So that's going to be a plus b. And then for a plus b squared, well, that's going to be equal to a squared plus 2ab plus b squared. Then our next one along here, so which is the a plus b cubed, following this pattern here, it's going to be an a cubed plus 3a squared b plus b 3a b squared plus b cubed. A to the power of a plus b to the power of 4. It's going to be similarly, I just need to stretch this out here. A to the power of 4 plus 4a cubed b, like so, plus 6a squared. I always struggle just trying to remember to minus 1 and add 1 here. B squared plus 4a b cubed and plus b to the power of 4. And then we can see our lovely answer that we've discerned above. A plus b to the power of 5. That's going to be a to the power of 5 plus 5a 4b, a to the power of 4, b plus 10a to the power of 3b squared plus 10a squared b cubed plus 5a b to the power of 4 plus b to the power of 5. The other question I think this said is we needed to expand a plus b to the power of 6. Well, there we go. We can do that based on there's a plus b to the power of 6 right there. So this would lovingly expand out to a squared plus 6a to the power of 5b plus 15a to the power of 4b squared plus 20a to the power of 3b to the power of 3 plus 15a to the power of 2b to the power of 4 plus 6a to the b, a times b to the power of 5 plus b to the power of 6.